Hello, my name is Sergio Armida and I will talk to you about polymer brushes, applications in biomaterials and nanotechnology. First of all, I need to tell you that polymer science or macromolecular science is a subfield of material science concerned with polymers, primarily synthetic polymers such as plastics and elastomers. The field of polymer science includes researchers in multiple disciplines, including chemistry, physics, and engineering. Research interest in surface-confined polymers has led to many novel approaches to their synthesis, characterization, and application. These surface-confined macromolecular architectures are referred to as polymer brushes. Attachment of the chains by one end in close proximity forces the chains to stretch out into an extended conformation to minimize segment. Polymer brushes are typically prepared through physisorption or covalent attachment. Physisorption, unlike covalent attachment, suffers to thermal and solvent instability. Covalent attachment can be achieved using grafting to and grafting from techniques. Grafting to requires the tethering of performed polymer chains to a surface. However, this technique often suffers from low grafting density, surface coverage, and film thickness due to the requirement of polymer molecules to diffuse through an existing attached polymer layer to reach the reactive sites, decorating the surface. Therefore, steric hindrance for surface attachment increases as the thickness of the polymer film increases. As a result of these limitations, the grafting from approach has become the preferred option for the synthesis of polymer brushes. This approach uses a surface immobilized initiator layer and subsequent in situ polymerization to generate the polymer brush. This is referred to as surface initiated polymerization or SIP. Polymer brush height is typically in the size regime of 10 to 100 nanometers. This is the depth that is typically considered as a surface layer in material science and proved by surface analytical techniques. The polymer brush community typically relies on ellipsometry, contact angle analysis, and attenuated total reflection Fourier transform infrared spectroscopy, or FTIR, where the information obtained is often restricted to bulk properties and global measurements. These techniques are more available and easier to execute than other principal surface techniques like X-ray photoelectron spectroscopy and scattering experiments. XPS is commonly used to accurately determine the elemental composition of polymer brush surfaces. This is a powerful surface technique that can be used to follow surface transformation. High-resolution regions scan of particular elemental binding energies afford not only the fraction of that element present, but also individual binding environments. As a result of only photoelectrons from the surface layer of atoms being able to escape, XPS characterization is confined to obtaining information at the surface of a material. Near-edge X-ray absorption fine structure microscopy provides quantitative analytical capabilities at the mesoscopic length scale. This has been developed into a powerful polymer characterization tool, combining atomic-specific soft X-ray spectroscopy with real space techniques. Atomic force microscopy has been commonly used to visualize polymer brush surface morphology and in some instances film thickness. In terms of medical devices, biomaterials have been defined as a non-viable material used in a medical device intended to interact with biological systems. Related to this, biocompatibility has been defined as the ability of a material to perform with an appropriate host response in a specific application, while biofilms are biomaterials that attach to our biomaterials that needs to solve a problem. All biofilms form with a basic sequence of events. 1. A conditioning film of proteins and other organic molecules forms on the biomaterial surface prior to microbial deposition. Microorganisms are transported towards the surface. Initial microbial addition occurs. Microorganisms strongly attach and anchor to the surface through production of an extracellular polymeric substance matrix. Adherent microorganisms grow on the surface and produce more EPS, and finally, isolated fragments of the biofilm detach and migrate. Device-related infection and biofilm formation can therefore cause severe problems, from loss of function of the device to lethal sepsis of the patient. Polyethylene glycol, or PEG, has been used for this problem. These brushes are typically prepared by grafting tool, however, and so will only briefly be considered here. Scientists describe how PEG brushes are used similarly to prevent protein absorption. The adsorbed biomolecule induces overcrowding within the brush, and the resulting osmotic penalty counterbalances the absorption-free energy of the biomolecule on the surface. Furthermore, the polymer brush increases the effective viscosity encountered by the biomolecule. Polyacrylamide, or PAM, polymer brushes have been prepared on silicon oxide wafers as a model substrate for silicon rubber using surface-initiated polymerization. The position and adherence of S. aureus, S. salivarius, and C. albicans was shown to be greatly reduced on brush-coated wafers compared to non-coated controls. The system was later transferred to silicon rubber and shown to reduce the addition of the same bacterial strains and be able in reconstituted saliva for 1 month, as shown in figure number 3. Polymer brushes can be designed to suppress non-specific addition of biomolecules to surfaces or promote a specific attachment of cell types to surfaces. Proposed applications for these biomaterials include diagnostics and cell culture. While nanotechnology is a widely used term with seemingly many definitions and uses, as polymer brushes possesses a dimension under 100 nanometers, they can be considered as falling under the realm of nanoscience. Polymer brushes, acting as well-defined and highly regular thin films, have been used to enhance sensors. The polymer brush can either act as the sensing element or improve the performance of the sensor. Examples include humidity sensors and photochromic ion sensors. The photochromic ion sensor uses spiropyran functionalized monomers copolymerized with methyl methacrylate from glass substrates. Upon complexation with different metal ions, there was a shift in the absorbance of the film that was ion dependent and easily discriminated visually, as shown in figure number 5. In addition to these examples, surface plasmon resonance and quartz crystal microbalance have been used as platforms to follow the synthesis and properties of surface-initiated polymer brushes. It is easy to envision polymer brushes being incorporated into these devices, in addition to other platforms such as surface-enhanced Raman spectroscopy to fabricate novel chemical and biological sensing elements. Electrochemistry has been used ionomeric polymer brushes, where the oxidation state of transition metal complexes trapped within brushes can be reversibly changed. Polymer brushes containing quaternary ammonium functionality and ionic liquid moieties have been examined this way recently, as shown in figure number 6. A group of researchers used cyclic voltammetry to cross-link a polyvinyl carbazole polymer brush, forming this basis of a polymer light-emitting diode. The current increased with each cycle, indicating the electropolymerization of the carbazole units. Polymer brushes can be used to stabilize colloidal particles. This has been extended to control and stabilize the formation of colloidal crystals. Colloidal crystals are materials with periodic structures prepared by self-assembly of submicrometric colloidal particles. Also, polymer brushes have been used in several areas to support metallic nanoparticles. Due to surface area considerations, these have been typically been performed from spherical substrates. It is evident that the use of highly functional, high grafting density, covalently attached surface layer is conceptually attractive. However, a question that often arises from polymer brushes being employed in different applications is a polymer brush really necessary? An alternative way of looking at this is to consider that if the application relies on modification of surface properties, what does polymer brush architecture gain over thin films or small molecule add layers? As polymer brushes find increased use in a variety of areas, the gain in performance from using a brush will most likely be application dependent. In summary, the field of surface-initiated polymerization remains vibrant, with polymer brushes being leveraged into many applied areas, a few of which have been highlighted in this video. Encouragingly, these applications appear to be driving a large part of the academic endeavor, rather than scientists making polymer brush systems we find intriguing and then trying to envision a use. Moreover, polymer brushes are gaining increasing traction in areas of chemistry, surface science, material science, nanotechnology, biomedical engineering, and biology. Indeed, opportunities exist for polymer brushes to have a synergistic effect at the interfaces of traditional disciplines. Many challenges persist, like routine characterization of polymer brushes on a molecular level, increased long-term stability of these thin films, determining the behavior of polymer brushes in complex milieu, and potential toxicity and biocompatibility of polymer brush-coated materials in vivo. Here are the references used in this video, and thanks for watching.